Very good morning to our Dr. TS Dr. Suhaila Ishak. Today I'll be presenting our group project 2 ALU design for RISC-V CPU for the course SKEE1233 Digital Electronic Systems. Okay, first of all, I would like to explain a little bit about the ALU design that we'll be doing for this assignment, which is we have this. So for the specification for this project is we have 4 bit of A input A0, A1, A2, A3, B0, B1, B2, and B3, which are 4 bits. Then T select and A select are 2 bits each, which used to select the input from A multiplexer and the B multiplexer. ALU operation, clock, and reset are 1 bit each. Next, the output are ALU out, which is 4 bits, and we ignore the carry out signal of this adder. From this project, the ALU operation switch 1 means is A plus B adder operation, and 0 is subtractor operation A minus B. Okay, looking at our circuit design in quarters prime line, we have 4 bit marks, and we have this 4 bit adder and subtractor, and the registers A select 1 and A select 0 switch to select the input for the 4 bit box. Has 4 bit of input, A1 has 4 bit of input, A2 has 4 bit, and same for A3. The selector is used to select which input they are going to take to output from the multiplexer. And B is also the same. Then after passing through this selector, we are going to pass through this 4 bit adder and subtractor, where input 1 from ALU operation is addition, and input 0 from ALU operation is subtraction. After the operation complete, it will pass through the register, where the clock and reset of the registers, and finally output from the register ALU out. Okay, looking at the 4 bit marks, here is our circuit design of the 4 bit multiplexer. This is the schematic diagram of the 1 bit multiplexer. We have 4 AND gate, 1 OR gate, and 2 selectors. Next, we are going to look at the 4 bit adder and subtractor. This is the 4 bit adder and subtractor circuit, where you can perform both subtraction and addition. Looking at the gate level full adder, the design is like this. The design of the registers consists of 4 D flip-flop, where each flip-flop takes in 4 input from the previous operation, and this is the clock, and then this is the reset, where a NOT gate is being used. If when reset is equal to 1, the whole operation is reset. When the reset is equal to 0, the operation runs as usual. Compile the final ALU design to see that if it is running correctly or now we'll run our timing simulation for the final ALU design. Now we can see from the timing diagram that the A select is 0, 1, which means it will select the A1 0, 0, 0, 0, and the B select is 0, 0, which means it will select the B0 1, 0, 1, 0. And then for the other operation is 0, which means it's a subtract operation. You can see that it outputs correctly. We'll run the addition operation for the ALU. Okay, so we can see now the A select is still the same, 0, 1, and then the B select is still the same, and it performs the addition operation and outputs 1, 0, 1, 0, which means this addition operation outputs correctly, and we can see it's the same for the second column and the third column also. After that, we will try the reset operation, which when there's a reset in the circuit, you can see that when reset is equal to 1, the output is 0, and when the reset is equal to 0, there's another output on the rising edge of the clock, and it has shown that the circuit or the final ALU design is running correctly.